Now that we've gone through the basic syntax and elements of Nyquist, or the SAL programming language, we're going to take a moment to talk more about programming philosophy and programming structure, and in particular, the idea of functional programming in Nyquist. Functional programming essentially means that you program in terms of expressions rather than programming in terms of variables and assignments and side effects. So in functional programming, programs consist of functions and values, not variables. And in functional programming, you compose functions. In other words, you call a function and you take the value that returns and use it as a parameter to another function. So you're just computing functions of functions of functions in order to get complex behaviors. In contrast, a more stateful or procedural program would take many steps sequentially and create many state changes by assignments to variables, and that would be the method to get complex behavior. So let's look at some examples. We're going to start with a very stateful program, and this is a bad way to write Nyquist code. It's here to basically show you what we are trying to avoid. In this program, we have a global variable called sum, and we have a bunch of helper functions that to initialize sum, to add a value to sum, and to multiply sum by a value. So using these, we're going to define my sound here to be the sum of a set of harmonics. In other words, sinusoids whose frequencies are multiples of some base frequency. So our base frequency is 440, and we want to have to add sinusoids to that with frequencies that are multiples. So that means 880, and what's 880 plus 440? 1320, I believe, and so on. And so we're going to do the addition in a loop. What we do in the loop is we compute 440 times I. That's going to be the frequency, the multiple. We use Hertzos to make a sinusoid at that frequency. We scale it by a random number, and we call add x to add that to sum. Okay? We loop through this for about 10 harmonics, and we take the result is going to be scaled by an envelope. So here's the envelope, and we use our multx helper function to scale the sum by the envelope. And now when we want to play this sound, we call my sound, and as a side effect, sum will be computed, and so we play sum. Now, what's wrong with this? In Nyquist terms, what's wrong with it is sum is a global variable, and when you play a global variable, that forces samples to be computed, but because the global is going to stick around, we need to save all of those samples. So we have to allocate a bunch of memory for the sound to be retained by this global variable. And that's inefficient and just undesirable. The other thing wrong with the program is if you try to understand it, what it's doing, you have to really understand what all these function calls are doing, add x and mult x. They're making side effects on a global, and it's a little hard to keep track of. Here's an alternate approach, and I'm not going to claim that this is necessarily easier to understand. This is a step in the right direction, and there's more to come. But for now, let's just look at how we can rewrite that program without using any assignment statements. It might not be obvious that you can even do that, but here it is. We first of all define a helper function, rand_harm, that just computes a sinusoid at a given frequency with a random amplitude. And the real work is done in harmonics. So harmonics is a recursive function. And what it does is, as a base case, it computes the fundamental frequency, rand_harm of hertz. But if this parameter n is not equal to 1, in other words, it's greater than 1, then what harmonics does is it computes rand_harm of the nth harmonic, and then it adds whatever comes back from a recursive call to compute n-1 harmonics. Okay, so you can see that if you add the nth harmonic to the sum of all the harmonics below n, then you get the sum of all harmonics. So that's the recursive step. And here in my sound, we call harmonics multiplied by envelope to get the scaling part. And then we can just play my sound. And this time, when we compute my sound, what will come back from my sound and harmonics is a lazily evaluated, in other words, unevaluated sound with the potential to compute all these harmonics. And the play command will force samples to be computed, but only a block of maybe 1,000 samples at a time that'll be written out, and the sound will basically be destroyed in the process of playing it. It will not be retained in memory, and that's what we want. Okay, but let's see if we can make this program a little smaller and a little neater and easier to read. So one thing we could do is relax our demand for purely functional programs. We can use some local variables and make a mostly functional program that's a little simpler. So here it is. We still have this harmonics function, and its specification is the same. We're going to compute n harmonics of this base frequency Hz. And to do that, we first of all assign the local variable SND to Hertz-Osk of Hertz times n, and that's scaled by some random value. Okay, so if n is 1, then we've just computed Hertz-Osk of Hz, and we're done. If n is greater than 1, then what we can do is recursively call harmonics to compute. We've already computed the nth harmonic, so we need to compute the all the harmonics less than n, and we do that with a recursive call, and we take that and add it into sound. So here's an assignment statement to SND to incorporate these new harmonics, and then finally we return SND. My sound is the same as before, play works as before, and because there's no global variable, what happens is, yes, we're using a variable, but we're not actually evaluating any samples, computing samples, so there's nothing to be retained by SND. Once harmonics returns, which down here, we get the result from harmonics. At that point, this variable SND no longer exists, so there's no need for Nyquist to save the samples, and Nyquist is pretty smart about figuring these things out, and so we get the right behavior. So basically, local variables are okay as long as you return the sound from the function before you play it or you evaluate it. All right, finally, I want to present the program the way I would actually write it. This is a purely functional program. It's very idiomatically a Nyquist program because rather than using recursion, which of course works, we're using a special construct called SIMREP. So SIMREP means simultaneous repetitions. What it does is it computes a number of instances of an expression, like this Hertz OSC times random. It computes many instances of that, all at the same time. It forms their sum and returns it. So that's exactly what we're trying to do here, is sum up a bunch of harmonics. I here is a loop variable. It goes from 0 to n minus 1, or whatever this expression evaluates to. And that's why we put I plus 1 here, because we want 1 times Hertz, 2 times Hertz, 3 times Hertz, and so on. Okay, and then once again, my sound is exactly the same. We just scale it by an envelope and we play it. And so this is not only, I would claim, a clean, short, concise, beautiful program. It has no global variables. In fact, it has no variables at all. So it's a good example of how you can write functional expressions, functional programs, just by defining functions and composing expressions together and get interesting behavior.